Okay, I think we should start now. Welcome everybody to Multiphysics 1. We have, I believe, all three speakers now. I've just been told there's a bit of a confusion between the Hoover app and what else is provided. So we have three speakers and they are going to be in this order: Marko Horvat, followed by Tom Flint, and then followed by Ms. Heba Alkafri, who is joining us online. So, well, Marko, would you like to do the presentation?
Sure. Thank you very much, Calvin.
Apparently, if you go beyond the X there, you're out of the camera shot.
So I should be within the X. Okay, so hello everybody. My name is Marko. Warm welcome to our online audience. I hope that at this point in time you should already know who I am. Today I'll be talking about conjugate heat transfer model and slight extension with the Vapour condensation model. The work presented here is a joint effort by myself and Prof. Jasak. He was doing more the implementation part of the work. I was doing more the application part. So yeah, let's just, how can I? This one. Yeah, this one doesn't seem to be working, but okay.
Sorry.
Oh, that's completely fine. Okay. So let's just jump right into it. Let's start with the fluid flow model. It's quite simple model. No, it's should be quite familiar to everybody here. It's just Reynolds average Navier-Stokes equations. We have a continuity equation which in incompressible form takes the simple form of just divergence being 0. There is also a momentum equation, all pretty, I'm sure, pretty much familiar terms in the equation to everyone here. We have the temporal derivative term, the convection, diffusion, and the forces on the right side. Key thing to note here is that we have used the Boussinesq approximation to take into account the density density fluctuations, and basically here the density is a function of the temperature difference. Finally, we have coupled this with the energy equation that again is pretty familiar. Can we go to the next slide? The solid thermal model basically solves the equation shown here, and what is important here to mention is that the solid part of the mesh and solid part of yes, the solid part consists of multiple materials and multiple blocks that have their own properties, and they are all merged together in this framework. Also, a boundary condition that is imposed at the faces that are turned to the environment or with constant temperatures are modeled by the Nusselt type boundary conditions, which is basically saying that the heat flux is proportional to the heat transfer coefficient and the temperature difference. Can we move to the next slide? Okay, so this the case that I will be showing you later was requested by a client. They are a very big civil engineering company, and they wanted from us to carry out heat transfer analysis of one of their products, and in this particular case is a window, and of course they wanted us to take into account the solar loading, and thankfully they had some experimental data with which we were able to not directly model the solar loading, but to substitute that with source terms into that are inserted into the energy equation. On top of that, the surface thermal radiation is modeled by the method of discrete ordinates that is written in for the final volume discretization. You can see the equation here, and of course the continuous direction variable S is written in the discrete set, and in the end the equation at the bottom is what is implemented in the OpenFOAM conjugate heat transfer solver. Yes, we can go to the next slide. The part that is implemented on top of the previous model is the vapor condensation model. This is quite simple model. It is just consists of one transport equation that is the vapor density shown on the top. And what we do in this case is we use the equation of state to move from the density to the pressure, to the partial pressure of the water vapor, and finally we compare this water pressure to the saturation pressure that is here calculated using this this expression given by Tettons. Of course, there are many experimental equations similar to this, but for the temperature difference that is expected in the case, this works quite well, and the expected error should be at the order of 0.1%. The mass of the vapor that is condensing in the model is then calculated by the difference from the difference of these two pressures. So if the difference is positive, then we declare that the mass of the condensed vapor is the difference divided by the RT, and if the difference is negative or zero, we declare that there is no condensation taking place. We can move to the next slide. So this is our geometry. So at the top two figures, you can see the volume part of the fluid, and on the bottom you can see the solid part. These are of course intertwined because the solid is the solid part is of course encapsulating the fluid part. So at the fluid part, what is important to take into to note here is that there is only a single connected volume. This is of course not the case for the solid volume, and you have of course the glass part of the window. Here they are split into two parts because the client wanted to have the left side of the window shaded, while the right side of the window was completely transparent, and the sides of the window are constructed from aluminum. We have of course the left part, the right part, the top, and the bottom. From the back side over here, there is an insulation that of course is modeled by the set of parameters that correspond to the material. You can see here that I mentioned the aluminum gap just by the side of the air volume where there is behind the glass, and this is the part that separates the inside of the window into two air volumes. You will see this in more details at the next slide. Yes, we can move. Okay, so this is the mesh. You can see all of the parts here combined. Let's start from the top left figure. You have the cross section that is vertical, and you can see that on the left side the glass, which is then in interaction with the front air volume, and then the aluminum part that I mentioned before that is separating the front air volume and the back air volume. The last part here is the insulation that is then interacting on the right side with the room and the room conditions that are specified there. The glass, of course, is interacting with the environment that is modeled by the Nusselt boundary conditions that I mentioned before. All the other section at the top and at the bottom are made from the aluminum, and you can see many openings. For example, the opening here, and there, also here, And these are the openings that are allowing the exchange of fluid between the front air volume, the back air volume, and the side air volumes where the fluid is able to enter and escape the window shown here. And as you can see, here are what is mentioned is the materials from which the parts are made of. And in this slide, you should also be able to see, but now we are just, no, it's okay. But we have one fluid region and we have 12 solid regions, and this fluid region has 22 patches because all of the interactions have to be, all of the interfaces have to be defined by a boundary condition. And at the solid part, there's much higher number, around 50 something patches. And just to mention that the solid when there is an interface between two solid parts, this is done by a GGI interface. And when we have interaction between fluid and solid, this is done by a so-called region-coupled boundary conditions that is implemented in OpenFOAM to treat this type of problems. Okay, when it comes to the simulation setup, I will show you snippets of the results for two different simulations. The first is with the solar loading that is modeled by introducing the energy sources. The sum of sources is mentioned here. It's 1,510 watts, and the room temperature and external temperature for these simulations were 20 and 26. So it's not very big pressure, very big temperature difference, but it's significant. The second simulation is without solar loading, and in this case, we were interested in seeing how the condensation part works, and this is the case where the condensation water vapor equation was used as well. Of course, this does not have the solar loading model because solar loading in this case works in our favor because it's less moisture getting condensed when we have additional heat coming from the solar from the sun. And this case doesn't have the temperature difference. It's pretty much the external and the room temperature are 20 degrees Celsius. In the table, you can see the materials and what properties did we use. In this case, yes, and basically what should be said is that the inlet and outlets are modeled in a way that we didn't specify like usually people do to specify inlets as fixed value and zero gradient of pressure, but we specified the pressure inlet outlet velocity for the velocity and total pressure for pressure. And in this case, you are not forcing the flow to enter at one inlet and exit at the outlet patches. Here you are. The flow is being driven by the buoyancy, and we didn't really know at the beginning what do we expect, which parts, which inlet and which outlet quotation are going to be real inlets and real outlets. Okay, for the reference, this is the same geometry but modeled by the client. They provided us with these results, and here I would just like to show you this, just so that you can see that we are not. To be mentioned here is that this simulation is two-dimensional, and this is, of course, very much simplified in comparison of what we want to do. And to be mentioned here that air is stationary in this simulation. The client used Bisco software. You can take a look at the website how this works. But basically, you have the same situation. So the left part of the glass is shaded. This is obvious because you can see that the temperature is lower at the aluminum parts and the insulation part, and also the fluid part. And the right part is transparent and fully transparent, and you can see the higher temperatures there. Please take a note what are the maximum and maximum temperatures here. So we can see 380 kelvins, and at the glass 341 kelvins. Of course, in our simulation, we expect lower temperatures because we have the fluid that is flowing between the two air volumes, and it's a 3D simulation in the end. We expect some changes. Yes, we can go to that. Okay, so this is now the results from the simulation. On the top part, you can see pretty much the same cross section you've seen before. The left part again is shaded, so you can see the lower temperatures there. The right part is completely transparent, so no a bit higher temperatures there. And you can see that now that the maximum temperatures are quite lower. At the glass, we have 324 kelvins. We had, I think, 340 kelvins in the previous example. And the maximum temperatures of the whole domain around 350 kelvins. And here we can take a little bit a better look at what is happening in the rest of the domain. So here you can see at the cross section A, this is the section going through the front air volume, while the big cross section at the back air volume. And of course, you have the vertical cross section at the right. Yes, we do. Yes, I was talking that we didn't know which patches were inlet and which patches were outlet, and this is just to show you that which patches we had, which openings we had. So at the bottom of the device, we had 3 openings where the flow could either enter the domain or leave the domain, and there were also 2 at each side. And as you can see, the lower parts are the lower openings were in the end the inlets, while the side openings were the outlets. Of course, the inlet flux, this is now the summed flux. It's 3 times 10 to the minus 4 meter cube per second in total. And this is, of course, balanced by the outlet fluxes. This is how the velocity fields look like. So the top, you can see the cross sections through the front air volume, and on the lower part through the back air volume. At the front part, I noticed that you have more 3-dimensional effects to the flow because the size is bigger for that air volume. This is completely different. At the back side, you have more 2-dimensional flow that looks much more regular. And the last part is for the second simulation, where the external and the room temperature were the same, and we were just taking a look what happens when we have the initial amount of water vapor in the system, and we would like to see what happens with this with the amount of density of the water density of the water vapor density inside of the domain. So we have carried out the simulation for a couple of hours. Here, the last snippet shows what happened. What is the situation after 5 hours? And here you can see the sum of the integral of the water vapor, and you can see how the water vapor mass evolved over time. And on the right side, you can see how much of the water vapor is flowing out with the fluid that exits the volume. Yes, and that would pretty much be it for the case. I would like to give a big thank to Prema Stilisa, who agreed to share the results with you today. You can take a look at what they are working on. It's quite impressive. They're building all of these big skyscrapers all over London, and it's quite impressive. Yeah, thank you very much. And are there any questions? Yes. Okay, sure.
Thank you very much for the presentation. Could you, I may have missed it, but was there any condensation in this,
So
this case?
as I said, it was a simplified model that we used, and basically the last slide that I showed, where we are presenting the how much of the mass of the water vapor was in the system. So this mass drops in time, and this drop in time is basically comes from two different parts. One is how much water vapor is leaving from the outlets, and the other part is how much is actually condensing in the system. So this is quite a simplified model here, because we are just comparing the partial pressure from the water vapor and the saturation pressure that comes from the experimental equation. Yeah.
So the fact that you have so many different regions and interface between solid and liquid, does that impact in any way your performance in terms of how the boundary conditions converge?
I didn't notice anything too significant. So yes, there are many solid volumes that are interacting also with the fluid volumes, and there are many interfaces in the system. But I have not noticed any significant performance issues, because these simulations were quite fast. So the mesh, for example, all together has around 5 million cells, and to reach the convergence for the steady state simulation that was only without the vapor condensation model, it took about 10 to 12 hours, no more. How many profits? It was done on. It was split on 8 processors, and the other simulation that was steady, that was transient with the water vapor model, it took a bit longer, but not more than 2 days. So nothing too crazy.
Hi, thank you for the talk. I was wondering again on the mesh, did you actually use a conformal mesh when you made it with the boundaries? Or did you use like the foam extend mixing style where you could sort of blur the...
Okay, so there are two parts when it comes to that. So I made the mesh using the condensed software pointwise, and some of the interfaces are conformal, some are not. It depended. At the beginning, I was doing everything conformal, but as client was expecting more and more interfaces, then I just wanted to make something that is quicker. So non-conformal was a better choice there. But there are no significant differences in how this operates, because even if the mesh was conformal at the interface, I used GGI to connect the solid regions and region couple to connect the solid and fluid region. And that this is the same thing I've done for the non-conformal interfaces. Anything else? No? Yeah. Maybe any questions from the online audience?
Are there any questions from the online audience? If you would like to type them in the chat box, that would be great, or unmute and say hello. Well, thank you very much for that. We'll move on to Tom.
Yes, thanks for having me. So I'm going to be talking about some phase field stuff, a bit different, I think, to some of the phase field stuff. See Professor Marshall here, I'm a big fan, so a bit different to the interface phase field stuff. Well, dynamic wetting type phase field stuff, but yeah. So I'm part of this. So I've put I'm part of a prosperity partnership which EDF Energy Fund. So that's why the slides of this, but it's a collaboration between University of Manchester, Imperial College London, University of Bristol, but they're interested in welding. Yeah, thanks. So basically I'm super interested in phase field modeling, and I'm going to be presenting 2 different phase field models in the slides today. And I guess the first thing to say is why bother. So our group at Manchester were interested in microstructural evolution. So the crystal structures that form in and around welds or additively manufactured components. So we want to know those crystal structures, because how those grains are oriented, the texture that evolves in the region, how those grain boundaries interact around the weld seam, tells you a lot about the lifetime performance of the components. Most of the work that we do is related to like nuclear components, so or other high value components where the structure might have to stay in service for decades without the possibility of being repaired. So we really want to understand how it goes into service in a really fundamental way. So that's why we do the modeling. And if we do the modeling, then there are a couple of different approaches you can use. So there's cellular automata methods, for example, which are a lot more computationally cheaper, but they don't capture so much of the interface physics. But they give you really sort of larger scales. They give you a lot of information. They rely on these simple rules that over a big large length scale, they reproduce the kind of features that you see in the solidification structures. And then but phase field models, they're a lot more physically justified, so a lot more thermodynamic, well, fully thermodynamically informed. And the really neat thing about phase field, the reason to do phase field modeling is you take a surface description of the free energy, which is really not well defined, and you convert it into a volume integral. So it's really a really powerful technique. So phase field models can be applied to a variety of different processes like fracture or interface dynamics. Anything where you've got a moving interface and a boundary, you basically take the interface and give it a width to give it a volume. So then when you look at the integral of the free energy functional, you then have it described as a volume. So a really powerful technique. So yeah, next slide, please. So yeah, the two phase field models I'm going to talk about then is one based on the multi-phase field approach of Steinbeck, and the other one's based on the continuum field approach of Néel-Moulins. So the approach of Steinbeck is a lot more, I'd say, is higher fidelity. That's the important thing. It's multi-component as well. So multi-component, multi-phase field method. And I'll show you the equations, but I've got that really nice now. So that's actually fully implemented. The phase field, the multi-component, multi-phase part is fully implemented. The only thing we need to do is couple that to thermodynamic databases to give us the driving forces. So the difference in the Gibbs free energy between an alpha and beta phase will give us the driving force for phase change, basically. However, as part of this project I'm on, we found that it's not really computationally tractable to look at larger components using that type of model. So I've been developing this other continuum field approach based on the work of Néel-Moulins. It's important. The multi-phase field approach is a lot more. It makes a lot more sense how you include the. So grains have 5 degrees of freedom. There's 3 rotation and 2 inclination. It's a lot more. Makes a lot more sense how to include all 5 degrees of freedom anisotropy into the multi-phase field model. It's not quite so clear in the, it's not as elegant in the Moulins approach, but it's still just as easy to make the mobility anisotropic, and that's probably the plan. Cheers. And also you can see the variational treatment's a bit different in the multi-phase field model as well. This is probably not that interesting actually. It's interesting. I find it quite interesting. But the phase field method is concerned with taking like a variational derivative. So what we're trying to do is we're on a free energy landscape and we're trying to find the quickest path down that hill, essentially. So that's what this functional derivative is. For the cases that I'm interested in, this Taylor expansion of this variational derivative just reduces to this thing in blue. So the derivative of the free energy functional, the integrand with respect to the phase order parameter, minus the divergence of that, the derivative of the free energy functional with respect to the gradient of that order parameter. So that relates back to what was on the other slide actually. So what I'm discussing now is like the multi-phase field approach, which is the higher fidelity approach. So if we do that, and this is like the interface component of the free energy. So there's a chemical component as well. Let's not worry about that too much. But the interface component for the free energy functional, if we were to do this variational derivative where our grain boundary energy is just a constant, it's quite nice. You get these like capillary terms and some bulk terms, really nice. However, in crystals, you have this anisotropic dependence on the orientation. So like for example, a cubic crystal or hexagonal body-centered cubic or a face-centered cubic will have 6 planes of preferential growth, whereas a hexagonal close packed will have 6 in the basal plane and then 2 that come out normal to the basal plane. So you can have these different anisotropic functions. But anyway, long story short is that if you have these so it can't be seen here, but there's the grain boundary energy is a function of the some isotropic component and then some anisotropic component, and the anisotropic component is a function of the gradient, which is horrible. So when you do this variational treatment, you have to take that into account. So it becomes really quite a long, quite a challenging derivative to compute. And also because we have multiple phases, we have to compute this derivative in the reference frame of each grain. So with each growing grain, each solidifying grain, for example. So it becomes quite challenging, but the nice thing is that I've done it. So it's next slide, please. Thank you. So we've done it. It was a lot of sort of pen and paper type horrible. I like it, but you know, not everyone does. So we've done it, and I define each grain with 3 Euler angles, and then rotate each grain. So it works really, it works really well. So we have now a multi-phase field framework in OpenFOAM with all 5 degrees of freedom. And so the only thing to do, I say only, but the thing to do is to couple this to thermodynamic databases, so that when we have the multi-component, the different how each chemical component is segregated, so it's like its solid and liquid component, we can get the difference in the Gibbs free energy there and I think I'll show the equations in a bit, so that'll be easier to see. But so next slide, please. Oh yeah, so this is the anisotropic part. So I was saying to Philip, I'm going for the record of the biggest term coded into OpenFOAM. So this is so when you do that derivative, when you have these norms, so this is for a cubic crystal. So and I also did some work where I made sure that there was no grid-induced anisotropy. So basically, when you have these different seeds and you rotate them a different amount, you still get the same crystal structure. So it's rotationally invariant. So I don't know why it always does this. It always renders the partial derivatives as these squares. I don't know why it does that. It's weird. But yeah, so that's that horrible anisotropic term. So this is the full framework then. So I've just put plus anisotropic because that's that term. I don't want to put that again. So it's fully multi-component. So we have this like a diffusion matrix. So we have n by n components. So n-1 by n-1. Multi-component diffusion terms we have to solve. I actually do it a bit differently because you have to then get the advective flux part. So it's so it's fully mass conservative. We keep all the flux, and I validated against this the multi-component diffusion part. We validated against this diffusion couple experiment where they put these two dissimilar multi-component alloys together and allow them to heat them up and allow them to diffuse together. It's actually, there's another term here because it's a function of the order parameter, but I'll not spend too much time on that. But then, so it's fully coupled to then a momentum conservation equation and energy transport equation. And yeah, so it's it works really well. As I say, we just need to couple to the thermodynamic databases, but that's that done. And yeah, sorry, next slide, please. So it works really well, 3D, no trouble or anything. I'll not spend too long on this, but the long and the short of it is that it's incredibly computationally expensive. So if I have n phases, I have n-1 solid phases, a fluid phase actually, and then I have an n component mixture. It's, in steel you might have 20 components, millions of phases. So it's really computationally expensive. So what we've done then is develop this other simpler continuum field, single component phase field framework based on the work of Mullins. Thank you. Oh, this is just some dendrites. So this is, these are just some dendrites growing where you have 3 seeds and they start off with, so they're in an initial temperature gradient. One of the seeds is perfectly aligned with that temperature gradient, so it grows preferentially. Then the other 2 are kind of rotated slightly, so they don't grow as easily as the one that is perfectly aligned. So that's just to show the framework in action. That's brilliant. Okay, so this is then the simpler approach. So this is based on the continuum field work of Mullins, and this is the code that we're going to release in the next couple of months. That's the plan. Because there's not, it's basically finished because there's not so much there's no coupling to do to any thermodynamic databases. Everything's kind of it's not as high fidelity, but there's not so much to do, so we've done it essentially. So but again, it's fully coupled. It's fully coupled to the momentum transport, energy conservation, and it's actually coupled to a volume of fluid type approach as well, actually. So the only the reason this isn't such a nice treatment is because if you have like there's I think this one's the energy bit, but when you have the you need like a semi-analytical solution to get the anisotropic dependence on the energy in this approach. So that's why it's maybe not as elegant, I don't think. But what we'll do is we'll have the grain boundary mobility as a that we can make that. There's basically no stress to make that anisotropic because it's outside the functional derivative. So the mobility is probably the most important thing, to be honest. So yeah, this is the code that will be released. We don't have a name for it yet. I don't know what we'll call it, but face fill foam's gone. So. But yeah, the working title is like CF beam weld foam. It's like continuum field, and it's built on top of this solver that released beam weld foam. So that's the working title. So yeah, I think that's. Oh, and this is just some examples. So this is actually what's coded into OpenFOAM. These are just what the equations are for that Moulin's type approach. And this is an example where we have an initial microstructure. There's a Voronoi tessellation algorithm, like utility that we've written as well, that you can seed an initial microstructure. And so this is just a microstructure held at a constant temperature, and the grain boundaries migrate due to the curvature, the local curvature of the interfaces. So yeah, the microstructure evolves due to that. And then I think on the next slide, yeah, and this is just applied to like a welding type example. So sort of like an this is nominally an electron beam weld. So there's like gas on the top and the bottom, and then initial microstructure, the heat source applied. You get some fluid motion that's basically not shown here, but you get fluid motion, Marangoni flow driving the currents, and it'll re-solidify. So it works really well, and it's a lot more computationally tractable than the multi-phase field approach, which is very expensive. Oh yeah, so then I just thought, if I had time, I don't know if I do, but I thought I'd say what else we've been up to. So with Philip Cardiff at University College Dublin and Galvin of Paravendon, we released this solver beam weld foam. So I do a lot of stuff on multi-component vaporization condensation with volume dilation and stuff. So there's this kind of simpler approach where you can assume that it's incompressible, and you just have this phenomenological recoil pressure term. So we basically released a solver that does that. So, and it has kind of a nice, maybe more like a different heat source description. And this is the code that the phase field one's kind of built on top. The single component one's built on top of. So that's some stuff I do as well. And the ray tracing, some good ray tracing discussions last night. So the other thing that we're going to release is this open source ray tracing code. So our group's interested in anything to do with like hot metal, basically. If it's hot, we're interested. Probably sounds weird when I say it like that. So we've got this ray tracing algorithm where we discretize the heat source and the angle that a packet of this energy interacts with a substrate. That tells you how much is absorbed. So you can, instead of having to have like a Gaussian heat source description, you can really have sort of fundamental parameters of the material and the laser wavelength, and that can. So here's like some rays scattering. Here's just a single path of a ray coming in and sort of bouncing around. So this is actually the thing we'll release next. Then it's the phase field one is the thing that we're going to do. So and then yeah, so that's that ray trace. Oh, this is just some nice videos. They just look nice. I think anyway. So yeah, this is like a laser drilling or a laser welding type application. So it's hard to see, but there's the rays that are bouncing around inside the keyhole there. So yeah, and then I think the next one's just applied to like a powder bed process. So similarly, like using the ray tracing algorithm to basically deposit the heat on the substrate, and then the fields will evolve. So yeah, works really well. It's pretty. It's parallelized and everything, so hopefully it'll be of interest to people, useful to other people looking at sort of manufacturing processes. Yeah, brilliant. Oh, and then the other thing that I do a lot of is like multi-component magnetohydrodynamics. So we developed this. So we're really interested in arc welding. Is another thing we're interested in. So when COVID hit, we kind of had some time to do some like different stuff. So me and my colleague sort of went through and derived this new magnetic induction equation where you have gradients and electromagnetic properties. So no one had looked at the magnetic. Okay, so if we basically rearrange the equation to be in terms of magnetic field strength instead of the field, well, H instead of B, and it works really well. It's really, yeah. So and then I think the next slide is just some. So we're able to predict these kind of when you have different properties on each side of the weld, basically we can predict these things. We did some X-ray. My colleague did some looked at these dissimilar welds in a synchrotron, and we saw these like weird structures that formed that the magnetic hydrodynamics was able to predict that you couldn't predict, because you have like loads of extra different forces like the Lorentz force. And what's nice about this actually is then you have everything's just a boundary condition, so you don't have to apply a heat source because you get it from the Joule heating term, so the J squared over sigma the electrical conductivity. So yeah, that works really well. And that's just, I think that's everything. Oh, and then this is just, sorry, I should shut up, sorry. So then I do some other stuff on, this is the multi-component where you actually take into account the vaporization term. So we use this to look at things like, just skip over that. So we use this to look at preferential element loss. That's what we're doing with this. So we use this to look at how in electron beam welding, you might get preferential loss of the lighter elements. So I just included some of the slides on all the stuff that we do because I thought I might not have time. But yeah, that's so this will be shown here that you basically, if you do an electron beam weld, you vaporize a lot more of the manganese, but you leave behind the molybdenum and the iron and all the other heavier elements. So this is a thermocapillary, a keyhole that forms an electron beam weld traveling along, and so I think the next, if you click, so this is like how we're depleted in manganese. That's the kind of stuff. And then the idea is to then couple this to all the phase field stuff. So we'll have this and then have the grain growth behind. And then just some like applying the same thing to some powder bed stuff. So the idea is to ultimately have everything all in the same sort of tool, similar toolkit that we can then release and people can use to look at these processes. I think that. So yeah, in summary, we've apart from the SID oil stuff that we do, we've developed these two phase field models, both implemented OpenFOAM. The idea is to release both of them, but certainly the continuum field model will be released in the next few months. The code's all ready. We just have to find some time to write up. That's it really. So thanks for. Oh no, I should say thank you as well. My colleagues Prateek Chantraj and Philip Cardiff and Galvin Parabender and Daniel Dreeland. They're the people I work with the most, and it's really sort of fruitful. And also just the community in general is really great. I think I used to write all my own finite difference codes for all this stuff, and it was since I started using OpenFOAM, everything's just really took off for me. So it's an absolutely fantastic community, and I'm like super grateful for it. So thank you very much.
We've got a question and we'll read that out.
Is it free?
Came up while you were about 3 slides ago.
Yeah. So it's free surface. Yeah. So we have. So the question is it free surface in the welding geometry, or the multi-phase approach includes the ambient air? Oh, okay. Yeah. So at the moment there's n minus 1 solid phases and 1 fluid phase, and then the fluid, if it's fluid or not, is basically determined by like a multi-component volume of fluid type approach that we've I don't know if it's normal, but that's what I've kind of added. I don't know, I just added it to the Mule's solver. So so it's but to make it fully thermodynamically consistent, the next thing to do is to make it n-2 solid phases, 1 liquid phase and 1 gaseous phase. That's the next. So then we can fully couple to the Gibbs free energies for every phase.
There are a couple of questions.
First of all, many thanks for this impressive talk. Really motivates to go further with phase field. I would be interested in the Beast Steinbach approach. Can you comment a bit on the software structure, on the object orientation, the level you have achieved there?
I'm not sure what you mean. Sorry.
I mean, this is quite involved in terms of how many equations you have to solve, and I mean, I am developing phase field method myself, so I would like to be interested if this could be extended towards a generic framework, unified framework. To what extent is that like thought of, or so that's the idea behind the question.
Brilliant. Thank you so much. So I think I hope this answers your question. So how the code is structured is that the phase field equations are only actually solved, or certainly the right hand side of the equations are only constructed near to the boundaries. So that's one way that we've kept the computational complexity a little bit lower in the Steinbeck approach, because obviously you have these like you could have thousands of phase field equations to solve, but it is just they are all solved at each time step. So it is, I don't know if there's a way to get around that, to sort of reduce the, to reduce that kind of computational cost of solving those. So yeah, how the code works is for every cell, I work out how many phases are local to that cell, and then create some lists that then I loop over to solve. So instead of solving overall, the sums that are over all phases, they're actually in reality, they're just over the local phases at each point, and that constructs the right hand side of the d phi alpha by dt equation. So yeah, but I think definitely, yeah, there are definitely additional things that could be done to improve that. I think the idea is to hope to get it basically kind of working and maybe not as efficient as possible, and then move on with the efficiency type stuff. Yeah, hopefully. Yeah, thanks.
Why do you need so many phases?
So we need so many phases because we have that many grains. So each phase is a different grain, so a different crystal in the solid metal.
But all crystals can't touch each other. There's a limit to how many crystals can.
Yeah, but so what you could do is you could have one phase here, and as long as it's what a lot of people do is they have like a coloring function. Yeah. So yeah, but the trouble with that is when then you include the anisotropy, what you're saying is that crystal over there that has an order parameter of whatever, and then this one are the same. What you're saying is they have the same anisotropy, they're aligned the same. So you're introducing an artificial texture into the material there. So what you could, yeah, you can do it, and if it's isotropic, so you don't have any, that's a very good thing to do. But if you have anisotropy and dendrites growing, then yeah, it's not. You'd induce artificial texture, because what you can show. I can't remember. You can show that you can have like just 10 phases in a cubic domain is enough. But then you'd only have 10 orientations of your grains. So
what's been done as regards validation, or did I miss that?
No, yeah, not very much. So there are some analytical solutions for phase field code. So for example, if you have if you have one phase fully encapsulated by another phase, the interface dynamics is like an analytical solution for the velocity. So that's what's been done in terms of applying it to an actual real system. So a real weld, that's like active work. So I've got colleagues at Manchester who are doing like EBSD maps, look at the texture around the welds, and I predict the texture. So for anyone who's not, metallurgists, which I don't know if I am, but you have these distributions of how the grains are oriented. So when something starts solidifying, if those grains are ordered aligned with the thermal gradient, those are the grains that will tend to grow. So you have these this distribution of texture in a weld. So they're the things that we'll get from the EBSD, and that's what we'll then use to validate this. So I'd say the phase field method is validated fundamentally on these real analytical solutions. But in terms of real experimental validation, it's very difficult. But that's something that we're in the process of trying to do. Yeah, and all of the sort of the fluid dynamics type stuff's validated against the like the Marangoni flows. We validate against the known, the well-known solutions. So the gallium melting case for the coarse grain stuff. Yeah, but the phase field stuff's definitely, I'd say, a lot more difficult to validate. Yeah. Thank you.
One more question online.
Okay, one more question on the. Kwang Wu Lee. One more question on the computing power. How big is the geometry? Okay. So typically it's of the order of a few millimeters, just because we have to have a phase field variable defined, all phase field variables defined in all of the mesh, basically. So it really does limit us to the maximum I've ever simulated is, I think, 2 millimeters cubed is the maximum volume I've ever simulated, and that means that's actually where the cellular automata methods come into their own, because you can simulate sort of huge domains with those, because it's not as computationally expensive. Yeah.
Do you want to answer?
Sorry, one more short question, maybe. The anisotropic parameter actually was unexpected for me. I expected it to be the mobility to have an anisotropy.
Oh,
you know,
sorry, yeah.
can you comment on that thing?
Yeah, sorry. So it's both actually. So I only showed, sorry. So I only showed the energy because that was the one. That's the one that you have to give the full variational derivative treatment to. So yeah, so both the energy and the mobility have the same anisotropic form. Yeah. Sorry, that's not clear. Thank you. Yeah. Well, thank you so much. Thank you so much.
Let me start here with a motivation behind this work. I'm showing here a collection of simulations performed in OpenFOAM. As you can see, different physics is simulated: heat transfer, fuel cells, bubbles or droplets dynamics. But then I pose a question here: what all these simulations have in common? Well, all these simulations are of a specific type of multiphysics problems, and that's what I talk about in my next slide. I start here with a quote from the well-known paper back in 1998 by Willer, Vapour, Jasak, and Horvat. Hope the names are pronounced correctly. In which foam was introduced. I read it out for you. The intention is to develop a C++ class library that makes it possible to implement complicated mathematical and physical models as high-level mathematical expressions. And we believe that nowadays, complicated mathematics and physical models would really mean doing multiphysics. And these are inherently and mutually coupled processes that have two main categories. I go over them quickly here. The first one, multi-field problems, in which we have a single continuum with subset of governing equations being coupled on a term-by-term basis. The second one, multi-region problems. We have a separated continua or disparate continua, as you see in this figure. We have two regions, for example, could be more, and each region has a set of governing equations, and the coupling is accomplished at the interface sigma via the jump and transmission conditions. But then today I'm focusing actually on the second type of problems, and that's actually what is common between all these simulations that we see here. They are all specific type of multi-region problems, the second type of multiphysics problems. But then, why reinventing the wheel every time we have multi-region problem? So we thought we could think of a unified framework with which you can implement all of these region-to-region coupling problems. Before I get into the details, here we would like to acknowledge that this work really stands on the shoulders of the various developments done by the community. We deployed a lot of the developments of Professor Hrvoje Jasak in Foam Extend, also his work with Professor Tokovic on the interface tracking library, Solids for Foam by Dr. Philip Cardiff, and time doesn't save me to read all these names out, but we are in continuous discussion and exchange with all these people, and also people from our mathematical modeling and analysis group. So we looked at the various developments of these people, which were like dealing with different types of problems, and we have tried to devise from these developments a unified framework that could deal with all kinds of multi-region coupling problems. I hope I haven't missed anyone or misspelled the names, but moving next to the outline, actually. Yeah, that was my introduction. Now for the rest of the talk, we first have an overview of the main structure of the code, which we call multi-region foam. The name not to be confused, hopefully, with other existing codes. Yeah, we take a glimpse at the code structure, what the user have to deal with, for example, main dictionary and case structure, a quick note on parallelization, then an application of this framework to implement an arbitrary Lagrangian Eulerian interface tracking method with a quick overview of the model, the methods, and the interface tracking class. And concluding by the test cases that I'm working on currently. Here we get into the details. The concept behind this framework, as I already mentioned earlier, there are all these different types of multi-region problems which have a generic structure that we would like to exploit. They have something in common, like a common ground that we break down into two fundamental classes. Here I mentioned the first class, region type. This class is derived from a registered IO object, and it holds a pointer to the mesh. Yeah, each of these each region type holds the physics specific to the region. It can correct its material properties, move the mesh, and solve itself also. The second fundamental class is the region interface class, derived from an IO dictionary. This one manages the coupling between the regions, which could be monolithic or partitioned. And it also allows for generic coupled boundary conditions. And generic in a sense that it implements, for example, a flux or jump, but does not know the physics behind it. It's generic. Is that jump coming from species concentration or from pressure jump at a capillary interface? That's really to be defined in a specific type class derived from region interface. Yeah, and these are the two main classes which are embedded into a multi-region system. And that multi-region system is building on a region type list and region interface list. And these are being instantiated from a dictionary, multi-region properties that I show in the next slide. For a simple conjugate heat problem, here we have two regions here. Fluid, which has a region type transport temperature. There is the solid, which is of conduct temperature. So these are the region types, the specific ones. And the coupling approach here, monolithic, is selected. It reads like this. So from fluid, from the fluid mesh, take the bottom patch and couple it with the top patch of the solid mesh with respect to temperature T. On the right side, you see the case directory, which is pretty much the same as the region structure that OpenFOAM follows. A note to make here that all like the utilities which have the minus region flag can also be used here in this case. So it's the same structure that OpenFOAM follows usually. Yeah, moving on to the design of multi-region foam and going over the main highlights of the code. We are using foam extend 4.1. As you might have already noticed, this the main idea is that this code is having object-oriented design, and it's physics guided. Here I'm showing some examples of implemented specific region types. Also for the interface, interface specific type. And yeah, the next point is the coupling and communication between regions is administered by the region interface class, also with a helper class called interface to interface couple manager. And that class gives you access to the information of the neighbor, like region, or the neighbor, like without thinking about what's the name of the neighbor mesh, what's the name of the neighbor patch. All of that is just accessed via this couple manager. Next, the interface to interface mapping, reused from solids for foam, which allows for different transfer and mapping methods. For example, direct map, GGI, and so on. The generic boundary conditions I have introduced earlier yeah, I think is here. Next one, parallelization, which we will talk about in a minute in the next slide. Can you still hear me? Because I got a note that. Are you still following with me? No.
You're absolutely fine. You keep, please carry on.
Ah, yeah. Okay. Yeah. Because I got a notification.
We're all still here. Don't worry.
Okay. Yeah. Okay. Yeah. So I was yeah, talking about the parallelization by global polypatch. Also, we'll talk about that. Yeah. Finally, the system solution and coupling method is coded in multi-region system. There could be used a partitioned approach by solving the regions one by one, or monolithic by assembling and solving a block matrix system. For parallelization, I would quickly here say that we need a phase-based interpolation between patches for the boundary conditions, and point-based interpolation, and there is mesh motion. And we use a global polypatch approach to do that in parallel. And this approach involves three steps, starting with mapping local fields from the local patches, the blue local patch, to the global patch, which is the red and the yellow ones. These are like, this is a global patch that every process involved here has access to. Then interpolation between the two global patches with the method of choice. And finally, mapping the interpolated global field back to the local patch. Yeah. Next is an application where we used multi-region foam for region-to-region coupling to implement an arbitrary Lagrangian Eulerian ALE interface tracking method. We have here two regions, say mesh A and mesh B. Every mesh or every region has the following set of Navier-Stokes equations, which are the well-known mass and momentum conservation equations in integral form for controlled volume V of T, actually, to indicate that volumes can change over time, and yeah, this like the surface or the mesh is moving. So in addition to the velocity fluid, we also have the velocity of the fluid. We also have the velocity of the mesh, W. Yeah, and using these first two equations along with the closure assumptions that I list here, we get into the interface equations, which are the jump and transmission conditions. For velocity, saying that there is actually no jump, its velocity is equal, is the same at both sides of the interface. The momentum flux is the same as is equal to the surface tension forces and the Marangoni effect. And there is an additional equation here to be satisfied, which is the space conservation law. Yeah, which ensures that the volume and mass is conserved during this motion. Here, shedding the light on some of the numerical aspects and the methods that we are using, which is based on the work of Hrvoje and Jasak, 2012. We use finite volume discretization of the bulk meshes, finite area on the interface, coupling by enforcing the interface equations that I showed. Yeah, the interface tracking algorithm is the control point algorithm. In brief, I describe it to you. In that procedure, we displace the interface mesh points, the black ones, with the help of control points, which are positioned at the center of the places. And then the movement of these points is such that the volume flux computed here compensates the mass flux that results from calculating the interface velocities. Yeah, then the interface mesh points are moved in point normal direction onto the least square plane led by or laid by these control points. Yeah, and this method is second order like second order mesh skewness correction. We use an enhanced backward differencing scheme from the last reference I have in this slide here. It's for time consistency to ensure that time consistency for moving meshes. Yeah, I think moving to the next slide. Yeah, here you see the interface tracking directory with dependencies to the multi-region form, which we have discussed earlier. Now, in addition to the interface tracking FV mesh class, which has support for multiple moving surface patches per region. Like multiple, we mean like the interface patch motion and also consistent motion of the neighboring mesh patch, which we call the shadow motion or the so interface and interface shadow patches. Yeah, and the moving interface patches class is actually where the ALE interface tracking algorithm is implemented. Yeah, I think that concludes the codes part. For validation, we looked for some typical bench model cases for testing solvers. The first case is a stratified flow scenario due to pressure gradient. Here the coupling is in tangential direction is assist. The analytical expression is available for the velocity profile and the results are in good agreement. The other two cases that I'm still working on, The first one on the left is single free rising gas bubble in quiescent water. We use a co-moving frame of reference. This is an experiment from the first reference here in my slide. The bubble is released as a sphere with zero velocity, then it accelerates and until it takes a final shape and reaches a terminal rise velocity value, which then could be used for validation. We use a 3D polyhedral mesh, as you can see in this photo here. And the second case is an oscillating droplet scenario, which has a similar setup for the mesh, except for the initial shape, which is an ellipsoid. And yeah, then the droplet or the bubble oscillates due to interfacial tension forces. Yeah, there are approximate analytical profiles available for this case, like under some conditions, like for envisaged fluids or for the limiting case of low or high viscosity of the fluids. There are multiple scenarios that could be simulated here. Also could be like tested with a free surface flow or with Newtonian fluids, or even introducing viscoelastic fluids. This work is in progress, and hope to get it done soon and publish it also. Yeah, and by that, I think I conclude my presentation. Yeah, thank you for attending and for your attention.
Right, thank you for a very good presentation there. Are there any questions either online or in the audience here? Got one from Lionel.
Regarding the grids, I mean the meshes, what tool do you use to create the polyhedral grids?
Did you catch the question, Heba? Have we lost you?
The question is a really quick question. What is the tool that you use to create the polyhedral grids?
Oh, for the polyhedral mesh, yes, we use the Salome here first to generate a tetrahedral mesh using a NetGen algorithm, and then you can use that tool IDS to form convert it in, and then the polyhedral convert it to a polyhedral mesh with a polydual mesh tool. Yeah. So yeah, Salome and polydual mesh.
Okay. Any other questions?
Yeah, I could share the name. I'm not sure. Yeah, that tool.
Oh yes, yeah. I guess you can read the question here, but I will just see if I can. Right, yeah. There's a question here which I'm going to read out for the benefit of people here. Thank you for the nice talk on the tool. I have two questions. How does it perform in comparison with the OpenFOAM multi-region solvers in terms of convergence and computational power? And is there a publication on this tool where I can read more about it? Anyway, Heba, would you like to answer those questions?
Yeah, maybe I'll start with the second one. For the publication, the tool for the meshing, or you mean the code that we are
I think
working
the code overall, I would imagine.
Yeah, the code overall is not published yet. Yeah, that's the work of multiple people, and I think we have to decide when to publish it. Yeah, so still there's no reference, I would say. And The second question, how does it perform in comparison with the OpenFOAM multi-region solvers? I think I still need to do a like study maybe about that before commenting or judging, because as you can see, it's still new and work in progress. So yeah, I would wait until I would really make a comparison and see and comment on that. Yeah.
Thank you. I've got a question related to that. What sort of computational effort do you need to do these calculations? Are you running them for days on big processors or minutes on a laptop or what?
For now, still like I haven't used like any like powerful or any cluster or something. I'm still running on my machine, like 8 processors. Yeah, the time is like 1 to 2 days, but yeah, that's what I have been doing so far. But yeah, maybe that's yeah, maybe it depends on the complexity of the simulation. But till now, I haven't faced that much complex situation where I have to run it for days or something. I haven't faced that yet.
Right, thank you. Are there any other questions online or elsewhere? Doesn't look like it. Well, in that case, can we thank Heba for her presentation and all the presenters?